In this tutorial, we're going to go over a test review in detail over all the questions, multiple choice and otherwise, for a test on exponential and logarithmic functions. And this is for a unit in a calculus and vectors course, so this is the calculus part. So we're also going to be looking at derivatives of exponential functions, but not derivative of logarithmic functions. The logarithmic functions are included because they're certainly very related to the exponential functions. And so in question number 1 here, in the first part of the multiple choice, we're asked if y equals mu to the power of t, and mu is a Greek letter. If you haven't heard it before, it's pronounced like a cow, mu. Where mu is a real number, we're asked to find dy dt. So the derivative of this function, any real number to the power of some variable, is the original function, so mu to the power of t, and then we multiply that by the ln of the base. So that would be the derivative, and just as a matter of form, constants are normally written before functions, so we would write the ln of mu first and the mu to the t second, so that's why it's written in this order, and that's why C is the correct answer for question number 1. For question number 2, y equals 7e to the 4x, and notice the difference here is the base is e, which is that base of the natural logarithm. So it's not a real number like mu or a half or 0.5 or something like that. And so we're asked to find dy dx and it says in simplest form. I'll talk about that in a moment. So the derivative of an exponential function is the original function, so we would write 7e to the 4x. And then you multiply that by times the derivative of the exponent. Derivative of 4x would be 4. Now, we don't have to worry about the ln part here. And actually, I'll put that in here for a moment anyway. But so we multiply, like here, this was the ln of the base. See, the ln of the base, well, the base is e. And the ln of e is 1. So that's why we don't worry about that. So that's 1, so we just need to multiply the 4 by the 7 over here to give us 28, and then e to the 4x afterwards. So 28 e to the 4x is the correct answer. C is actually a correct but unsimplified answer, because this is essentially what we have up here. It's 7, and then the ln of e, and then that 4, and then e to the 4x. So that actually is the same thing, it's just not simplified. 28 e to the 4x is the simplified answer, so A is correct for number 2. For number 3, log base e of p. Log base e is the same as ln, so that is equal to ln of p. So D is the correct answer for question number 3. For question number 4, you have to remember your rules for logarithms and ln. So let's take a look at the exponent here, the log of 10 to the 5th. If I write the log of 10 to the 5th. Now notice that there's no base specified, so the base is actually 10, so there's actually a 10 right here. And if the base of the logarithm and the base of this power are the same, then that just equals the exponent there in that power. The law is normally written like this: if you have the log base a of a to the x, that equals x. So this whole exponent here is actually just equal to 5. So this is actually the ln of e to the 5th. Now ln, remember, is the same as the logarithm base e. So if I write that ln is log base e, and then we have e to the 5th, then by the same reasoning as over here, if those are the same, see the bases are the same, that just equals the exponent. So that would equal 5. So 5 would be the correct answer for question number 4. And for question number 5, the last multiple choice, if R naught or R sub 0, and if you haven't seen R naught before, naught or sub 0 means usually initial amount of radioactive Rutherfordium-261, and we're told the half-life is 81 minutes. You're asked then, which of the following represents a formula for the amount after t number of minutes? So E is the correct one. The amount at any time is the initial times the half to the power of, and it's always the time divided by the half-life. There is another correct way to write this. You also could write it like this, and there's other answers here that are similar to this. You could write this as R of t equals R naught, And instead of a half, you could go 2 to the negative 1. So what that changes is then the exponent would be negative t over 81. So that's another correct way to write it. And if you look over here, let's see now. E is kind of close, except, or B here, sorry, but there's an E there instead of a 2. This one here, actually I didn't put another one right that. Again, I got e to the t over 81. This isn't too close really. Instead of t over 81, it's negative 81t. So E is the correct answer here. This one's kind of close, except notice that I've got the same exponent here, but if this was a 2, then it would be correct. But I have a half there. So E is the correct way to write the formula. But this one would be also correct. In part 2, the first of some questions to show some work are asked to find the derivative of y to the 10th using the first principle's definition of the derivative, dy dx is the limit as h approaches 0 of f of x minus h minus f of x over h. And in part 2 here, first of several questions to show some work. In the first one, it says find the derivative of y equals 10 to the power of x using the first principle's definition of the derivative. And you're allowed to use this, and we do need this, the limit as h approaches 0 of b to the h minus 1 over h is equal to the ln of b. It doesn't really matter what base you put in here. Down here I call it a, b. It doesn't really matter. So here's the first principle's definition of derivative, and our function is y equals 10 to the x. So f of x plus h would be 10 to the power of x plus h, and f of x would be the 10 to the x. And so you can factor a 10 to the power of x. That's a common factor in both parts here. So we factor that out, and remember, to know what's in the top here in the numerator, you divide each of these by 10 to the power of x. So for example, when I'm factoring out of the 10 to the x plus h, when you're factoring out a 10 to the power of x, remember, dividing powers of the same bases, you subtract the exponents. So it'd be 10 to the x plus h minus the x, and of course those x's are opposites, they add to 0, and so that's why we get 10 to the power of h right there. And similar to, if we're factoring a 10 to the x out of a 10 to the x, you would get a 1. So let's do a little erasing here. Just get rid of that. There we go. So this is what I have now. Now this is why we need this concept up here. I'm going to factor the 10 to the x out of the limit. And so the limit as h tends towards 0 of 10 to the h minus 1 over 10 would equal the ln of 10. Just like over here it says the limit of a to the h minus 1 over h as h tends towards 0 equals the ln of a. So it's just the ln of the base. So the base was 10, so it would be equal to the ln of 10. So the derivative would be 10 to the x ln 10, or we could write it as ln 10, 10 to the x. So in question number 2, we're asked to differentiate each of the following. And in A, we've done this a couple times already. Y equals 6 to the x, so the derivative of that would be 6 to the x times the ln of 6. And of course we could also rewrite that as the ln of 6 times 6 to the x. That'd be the same thing. In B, we have the function h of x equals negative 5 e to the negative 7x squared. So the derivative would be the constant negative 5 times the derivative of the e to the negative 7x squared. So it will be e to the negative 7x squared times the derivative of the exponent, the derivative of negative 7x squared using power rule. 2 comes down and multiplies by negative 7 to be negative 14. Subtract 1 from the exponent, so it would be a 1 there. We don't have to worry about multiplying by the ln of the base because it's e. So multiplying negative 14 by x by negative 5, we get 70. So it's going to be, and don't forget the x here, 70x e to the negative 7x squared. For C up here, we have a product. here's a cosine function multiplied by a power of e function. And so we use product rule. So the first function is this negative 3 cos 5x. So we write negative 3, and then differentiating the cos 5x, we would get sine 5x times 5 being the derivative of the 5x. So that's the derivative of the first function times the second. Now, you notice I've got a minus there. If you remember the product rule, I'll write this above it here. So it's actually plus, and then there's a negative, the first function, cos 5x. And so that's the first part of the second half of the product rule. And so instead of writing plus a negative 3 cos 5x, I'll just write minus 3 cos 5x. And then we got to multiply that by the derivative of the second function. So e to the 2x to the fifth would be e to the 2x to the fifth times the derivative of the exponent. So that would be 10x to the fourth. So there's the 10x to the fourth. And so just to simplify this a little bit, I'll multiply the 5 by the negative 3 to give us negative 15, and then sine 5x e to the 2x to the fifth. And then I'll multiply the negative 3 by the 10x to the fourth. So negative 30x 10x, negative 30x to the fourth, and then my cosine function and the power of e function. And that's the end of it. In question number 3, we're asked to find all local extrema for y equals 5x cubed e to the 3x plus 1, and then determine the type of extrema. That means whether the local minimums or local maximum points. So extrema occur, or maximums occur, where the first derivative has a value of 0. So that's why we're going to find the first derivative of this first. So the derivative of 5x cubed would be 15x squared using the power rule. Remember, 3 times 5 is 15. Decrease the exponent by 1 from 3 to 2. Times my second function. This is a product. So that's the first part of the product rule. Plus, the second part will be the first function now, multiplied by the derivative of the second function. Now, the derivative of e to the 3x plus 1 would be e to the 3x plus 1 times 3, 3 being the derivative of that exponent. And the only thing I would do to simplify this now, I'd multiply the 3 by the 5x cubed to make 15x cubed in this term here. This term's fine as it is. And so I'm going to set this equal to 0. And we can common factor a fairly large factor out. 15, of course, is a coefficient of both, so 15 will factor out. There's an x squared here and x cubed, so we can factor an x squared out. Remember the lowest common power to all of them. And there's an e to the 3x plus 1, so we can factor that out too. So the common factor is actually this first term. And so if I factor the entire term out, I get a 1. Remember, you're actually dividing. This divided by this is 1. And the only difference on the end here is there's an x cubed instead of an x squared. So x cubed divided by x squared would be an x. And I got 3 different functions here. The 15x squared I'm going to say equal to 0, the e to the 3x plus 1, and the x plus 1 as well. Now the reason I've got a not equal to here is because there is no solution to this. E is a non-zero number, and you can never have a non-zero base raised to any power to give you 0. So there is no solution from this. But there is from these. So 15x squared equal to 0. The first thing I would do to solve for x here is divide out 15. And of course those 15s divide out, and I get x squared equal to 0. And so I would solve that by taking the square root of 0, which of course is 0. So that's where this 0 comes in. The last one here, x plus 1 equal to 0. If we isolate for x, we get negative 1. So at 0 and also negative 1, there are potentially local minimums or local maximum values, points. Now I'm going to eventually need the function values for these because it says it implies local extrema means a whole ordered pair, not just where the x coordinate occurs. So I'm going to put 0 and then also negative 1 back in my original function. So I'm going to put 0 here and there. So 5 times 0 cubed times e to the 3 times 0 plus 1. So 0 cubed is 0. So it actually means it's going to have a value of 0. It would actually be 5 times 0, and this would actually be e because 3 times 0 is 0 plus 1. This would actually be e here, but 0 times e is just 0. So if x is 0, y is 0. So this is actually the origin. So there's a potentially local minimum or maximum point at the origin. And also do negative 1. Put negative 1 here and here. And this looks like negative 1 cubed is negative 1 times the 5 is negative 5. And in the exponent here, 3 times negative 1 would be negative 3, plus 1 would be negative 2. And you'll see that lots of math teachers would like you to write that with a positive exponent. So instead of writing as e to the negative 2, write it as, well, negative 5 over e squared. So that's the function value or y value where x is negative 1. Now, the type of extrema, we can use the second derivative for this. This is called the second derivative test. And the second derivative test says if we have a place where there's a local minimum point, and if I draw a couple of tangent lines here, I meant that to be a little higher, like that. Then notice remember the slope of those is the same as the value of the derivative. They're going from negatively sloped to, actually that would be 0, to positively sloped. And so if it goes from negative through 0 to positive, that means the second derivative is increasing, so it's positive. Positive second derivative means we have a local minimum point right there. If it's a case where the graph is concave down, you think of going from left to right, the value of the derivative goes from being negative, and I want that to be a little higher, through 0, oh, that's positive. Positive through 0 to being negative on this side, so the second derivative is getting smaller. A negative second derivative means you have a local maximum point. So that's the second derivative test. Now I'm going to just pause and erase all those. So to calculate my second derivative, I'm going to go back to this line here and differentiate this. And this is a product. There's a 15x squared e to the 3x plus 1. And this is another product, 15x cubed e to the 3x plus 1. So I'm going to have two different product rules, and that's why there's actually 4 different terms here. So the derivative of 15x squared would be 30x times e to the 3x plus 1. And then plus, and the second part of the product rule would be 15x squared here times the derivative of e to the 3x plus 1, which would be e to the 3x plus 1 times 3, just like it was over here. So this up to here is a derivative of that. So now we need to differentiate the second product here, this guy right here. So 15x cubed's derivative would be a 45x squared, power rule again, times the e to the 3x plus 1 function, and then plus, and the first function now, the 15x cubed, times the derivative of e to the 3x plus 1 again, which would be e to the 3x plus 1 times 3. So this would be the derivative of that guy right there. And I've got a little simplifying to do. 3 times 15x squared would be 45x squared. 3 times the 15x cubed would be 45x cubed. And these are like terms. They're actually not just like terms. They're actually the same term. So we can add those together to get 90x squared e to the 3x plus 1. This guy doesn't need a simplifying, neither does the one in the end. And I'm going to factor this before I start checking the second derivative at 0 and negative 1. I'm pointing this 0, that 0 there actually. This line wouldn't really be necessary. I just find it a little easier to substitute the values in to determine a value if it's in a factored form as opposed to not. Okay, so if you didn't do this line, it really wouldn't be a big deal. You should get at the same answers, of course. So there's a pretty big common factor here, like there was for the first derivative here. 15 goes into all of those. There's an x squared, and x cubed, so we can factor an x out, and as well we can factor the e to the 3x plus 1 out because it's common to all three terms. So there's 15x e to the 3x plus 1 is a common factor. So it's almost the entire factor here, except 30 divided by 15 would give us the 2. See, we factored the x out, e to the 3x plus 1, that's why it's just a 2 there. And the second term, 90 divided by 15 would be 6. X squared divided by x would be x, and we factored the e to the 3x plus 1 out. And on the end, 15x cubed, sorry, I don't know how I could actually look at that and say 15. 45x cubed divided by 15x would be 3x squared. 45 divided by 15 is a 3. And again, we factor the e to the 3x plus 1 out. That's why there's no e to the 3x plus 1 here. So there's my factored form of my second derivative, and I'm going to substitute 0. Let's start with the 0 here. So if we put 0 here, 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 and here, all those places. So there's all the zeros substituted in. So as soon as I say 15 times 0, I know it's a value of 0. I don't really need to evaluate. This would be e in the brackets here. This would be 0, this would be 0, this would be 2. So it would be 2 times e times 0, which is 0. Now, if it's 0, that means that there isn't going to be a minimum or maximum there. That's a possible point of inflection. Okay, so and the way you could check that is if we could find the value of the second derivative to see if concavity changed, if it went from negative to positive second derivative or the opposite, by substituting a number a little below 0, a little above. So I'm going to substitute negative 0.1 in, and then positive 0.1 down here. So I put negative 0.1 here, 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 and here. So there's all the substitutions right there. And evaluate this, and you may as well use a calculator for this. See, 3 times, well, actually in the exponent there, let's start at the beginning. 15 times the negative 0.1, negative 0.1, so that's why there's a negative 1.5 at the beginning. 3 times negative 0.1 plus 1 will be negative 0.3 plus 1, which would be 0.7. And at the end here, plus 6 times negative 0.1 plus 3, so we need to evaluate this whole thing, negative 0.1 squared. So that's where the 1.43 comes in. So it's negative 1.5 e to the 0.7, and then times the 1.43. Well, actually, I guess I didn't do the entire calculation here. I left it as a power of e. See the negative 1.5. You don't really need to do that. 1.43. So there's my negative 2.145 e to the 0.7. See, e to the 0.7 has to be positive. So this negative here is what means it's less than 0. It's concave down. So if you did the whole calculation, you'll get this, but they're both negative values. So less than 0. So now we're going to do positive 0.1 and instead of negative. So this line looks the same as this one, except you get rid of the negatives. Positive, positive, positive. And so we end up with a positive value. I won't go through the calculation of that one. It's positive, so the graph has changed to be from concave down on one side to concave up. So there's actually a point of inflection where x is 0, not a local max or min. Now we'll do the negative 1. Remember, the other place was negative 1 here. So if we put negative 1 in place of x in our second derivative, and I could use the factor form. I didn't bother here, but I could have just used the factor form too. You'll find, well, this is actually 15 times negative 1 is negative 15. In the brackets here, well, I guess I did use the factor form, didn't I? Plus 6 times negative 0.1, and then same idea here. Really just need to do this to find the sign. So that's where the negative 1 comes from. And so negative 15 times negative 1 is positive 15, again, be over e squared. That's positive. So that's going to be greater than 0. So that means that if it's greater than 0, it's concave up. So there's a local minimum there. It looks like that. So there's a local minimum at this negative 1 comma negative 5 over e squared point. And the 0, 0 wasn't a maximum. It's actually a point of inflection because concavity actually changes there. And just to show, I graphed this in Desmos, so I'm going to bring this over. There we go. So there's the local minimum point at negative 1, and at 0, 0 you can see the point of inflection. The concavity changes from down there to up here, so that actually is a point of inflection there. Question number 4. Curium-250 has a half-life of 90 years, and we're asked in A to determine a formula that represents the amount remaining after t years for a 25 milligram sample. So I'm going to call C of t, let C of t represent the amount remaining after t years. And so here's the formula. C of t would equal the original amount, kind of like that Rutherfordium question at the beginning or the end of the multiple choice, times a half to the power of t over the half-life. So if we're told the half-life is 90, then we would put 90 in place of H here, and our original amount is 25 milligrams, so 25 milligrams goes in place of C naught. So that's the formula, and the one we'll use in the question below. So in B it says use your formula, in B and C as well, to find the amount left after a century. Now a century is 100 years. So in our formula here, from up here, we're going to put 100 in place of time. So 25 times a half to the power of 100 over 90, and maybe I'll bring my calculator back here. So 25 times a half, or 0.5, to the power of, and in brackets I'll put 100 over 90. Okay, so there's where my 11.6 comes from. Now, when you're evaluating this your calculator, make sure that you're careful with the brackets. A lot of people, here's a common mistake some people would do probably. Delete, there we go. Is forget to put brackets around that 100 minus 90. See, now that says that's a really small number. That's 0 and 30 zeros, and then 219, etc. See, I've actually evaluated 25 times 0.5 to the power of 100, and then divided the whole thing by 90. So that actually is the same as if I had done this. This should work out to be the same thing. I'll be surprised if it doesn't. Pretty sure I know how my calculator works. Yeah. So I've actually done the 0.5 to the power of 100 times the 25 and divided the whole thing by 90. But you see the 90 is supposed to be just divided into 100 and then that power of a half evaluated. So make sure you know how to use your calculator. So 11.6 milligrams is what's left after a century or 100 years. And in C, you're asked at what rate is the isotope decaying after 50 years. So here's our formula up here. The rate, of course, we need the derivative. So let's differentiate this function. This is a function from above. So the derivative would be the original function, and then multiplied by the ln of the base, and then multiplied by the derivative of the exponent. Now the derivative of t over 90, you could think of that as 1/90th t. And so the derivative of that would be 1/90th. So that's why we multiply by the 1/90th on the end. So just to simplify the derivative before we evaluate it at 50 years, so I'll multiply the 1/90th by 25 and write it as 25/90ths. Ln of a half times the 1/2 to the power of t over 90. And so there's my derivative. Now, I just noticed I didn't simplify the 25 over 90, so if you wanted to reduce this, this won't make a difference in the end calculation. But 25 and 90 both divide by 5 evenly, so we could write that as 5/18 ln a half times a half to the power of 50 over 90. That's how you evaluate it. And of course, so this is the guy I'm talking about right here. I could have written that as 5/18. If you're downloading the PDF, I will certainly simplify that before I upload it. So to evaluate this, maybe I'll do that in my calculator here too. So so we've got 25/90ths or 5/18 times the ln of a half, so ln of a half or 0.5 times 0.5 to the power of, remember I was talking about making sure you put brackets around the exponent, so 50 over 90, I guess we could simplify that too, but we're evaluating this numerically anyway. So you get negative 0.13. Of course, negative rate means it's decaying. It's becoming less of it all the time. So the isotope is decaying at a rate of 0.13 milligrams per year. Now, decaying means it's going down. So you wouldn't say it's decaying at negative 0.13 milligrams per year, okay? Because the decaying implies a negative. And question number 5, on April 26, 1986, the nuclear power station in Chernobyl. Question number 5. On April 26, 1986, the nuclear power plant in Chernobyl, Ukraine suffered a meltdown. This is considered the worst man-made natural disaster in mankind's history. Question number 5. On April 26, 1986, the nuclear power plant in Chernobyl, Ukraine suffered a meltdown. This is considered by most to be the worst man-made disaster ever. One of the radioactive isotopes that were released into the atmosphere that day was cesium-137. And it says in 5 years after the disaster, only 11% of the cesium radiation had dissipated. So you're asked, what is the half-life of cesium-137? So we're going to let C of t represent the percentage remaining after t years. And so this is our formula that we used a couple times already. So that's what's going to model the data. Now, if 11% is dissipated, C of t represents the percentage left, not what's dissipated. So if 11% is gone, then there's 89% left. So 100 minus 11 would be 89. So if I use, now we don't have a certain amount like the 25 milligrams in an earlier question. So I'm going to use C naught to represent 1 being 100%. And so we're told then after 5 years there's 89% left, so C of 5 would be 0.89. So in the formula we'll put 0.89 in place of C of t, and then C naught's 1, and then it's 5 over the half-life. We're trying to find the half-life. 5 years is the time. So now I'm going to drop the 1 here. And I'm trying to isolate for h here, so I'm going to isolate for 5 over h first. So I do that by converting from exponential to a logarithmic form. So the 5 over h would equal the log of the 0.89, base a half. Base of the power, base of the logarithm are the same. Now we're trying to solve for h here, so what I'm going to do both sides is I'm going to multiply by h here. So this whole logarithm gets multiplied by h. So those h's divide out, and so in order to solve for or isolate for h now, h is multiplied by this whole logarithm, so h would equal the 5 divided by that logarithm, which is what's given right here. Now, if we evaluate that, and maybe I'll bring my calculator over and do this, so we have 5 divided by the logarithm, and we do evaluate the logarithm here, base a half, as the log of 0.89 divided by log of a half. If you happen to have a calculator that actually you can change the base, I only have base 10 and base e on this one, so you could do that certainly. So log of a half, or 0.5, close bracket. So 29.74, so very close to 30 years. So the half-life of cesium-137 is about 30 years. And last question here, B asks, how long will it take for the amount of cesium-137 to drop to 10% or less of the original amount released into the environment? So here's our formula from up above here. Remember up here we found that the half-life is 30 years, so that h is going to be 30. So now to 10%, so C of t would be 0.1, 10%. So I drop the 1, and again I'm trying to isolate for t in this case. So the t over 30 would equal the log of 0.1 base a half. And so I'll solve for t by multiplying both sides by 30. So now I don't have much room here, but on the right I'm going to multiply that logarithm by 30. So those will divide out. And so t is 30 times that logarithm. And again, maybe I'll bring my calculator one more time. So 30 times the log of 0.1 divided by the log of a half, log 0.5. So 99.7, so pretty close to 100 years. So it would take about 100 years for the cesium-137 to drop to 10% or less of the original amount that was released into the environment. And that's the end of the test review.